if we can catch up.
Sure. So the next talk is going to be accelerating HPC and DL applications using DPUs and efficient checkpointing. And Dr. Donglai will be presenting that. He is the chief engineer at Xscale Solutions and leads company's R&D team. His current work focuses on developing scalable, efficient libraries, checkpointing and restart libraries and performance analysis tools for distributed and parallel HPC and deep learning applications. So he has a vast amount of experience, more than 20 years of industry experience in engineering management and development of computer systems. He has he has 10 granted US patents and published more than 30 technical papers or book chapters. And he's an alumni of, MVAPICH team, and he has a PhD degree in computer science from the Ohio State University. So
thank you, Amir, for the introduction. And so I will try to see, because I prepared for 5 minutes now, less than 20 minutes. So I will try to recover as much as possible. I will skip some of the slides I prepared. Okay. So
your slides are cutting a little bit. Is it just for me, or other people are also seeing that?
Looks okay right now.
Okay.
Okay. Thank you. So I'm going to discuss our products, from Xscale. Today, specifically, I'm going to focus on accelerating HPC as well as DL applications using DPUs, as well as doing efficient checkpointing. And I'll give a brief overview of our company. Then I will discuss some of the existing product like Xscale HPC as well as Xscale AI packages. I will just touch them briefly. Then I will focus on more the two new products in the pipeline. One is the MVAPICH DPU. The other one is SCRX. And our company is relatively new, but has been there for a few years. And it's a startup. We focused on bring innovative and efficient end-to-end solutions and services, especially for the high end. And we provide commercial support as well as training for state-of-the-art communication libraries. Especially we focused on MVAPICH and MVAPICH 2 libraries and its derivatives families, including the X, the GDR, AZA, AWS, and so on. And we also has a product or packages supporting big data libraries. All of that are related to our RDMAs. And so we provide this service, commercial service, currently to federal national labs, as well as international supercomputing centers. And we are a winner of multiple DOE SPUR grants for R&D, and we are a silver member as an independent software vendor of Open Power Consortium. More details can be found in our website of the company. And next, I'm going to touch just briefly on the two existing products. And one is HPC and the other one is for AI package. So the HPC, for this one, we mostly focused on the providing commercial support for this. We fine-tune as well as customize this MVAPICH library and its families to whoever the customer orders to be. And we actually currently have a stable and growing list of customers. And the next, I'm touching on a little bit on the Xscale AI solutions. And this one is we, of course, built on top of the MVAPICH libraries. It's an integrated package to support the popular DL frameworks, including TensorFlow, PyTorch, and others. Okay. And one of the special tools we put in here is integrated profiling as well as introspection support for DL applications. And it provides cross-stack of the DL, doing performance analysis in a visual manner, which help the end user to understand and tuning their DR application for performance as well as scalability. And currently we target for both CPU-based as well as GPU-based DL training. We are built it to order. So for customer, it's out-of-box optimized performance solution. And we also built so that it's easier for customer to install and deploy. It's a single click. Okay, save a lot of hours for setting it up. And we currently support open power as well as x86 platform. And the network technology we support InfiniBand is InfiniBand, Rocky, and NVIDIA NVLink. And the next few slides, I will just show some of the benefits, okay, and capability of this package. And so this one is using the ImageNet as that AI application. And as you can see, the emphasis here is the scalability is really good. Okay, as you can see, every time you double it, it's almost double the performance. I mean, from the image per second count perspective. And as a result, it's always all the way up to 1600 GPUs. And as a result, the overall execution time is cutting down significantly. For 1.2 million images, we can do it in less than 5 minutes. Okay. And here, just touch on a little bit on the DI, the Deep Introspect toolbox. Okay, and this is the front end. And this tool basically collect all in relative information profile as well as stacks for whatever happened during your application run. Focus on the communication part of it. And this is just one of the stats we collect. We showing here for MPI reduce, because the all reduce is the most important communication pattern used in most of the DL frameworks. Okay, and I will not explain all the box because people will get their hands trying, will understand what's going on. But I will just focus what kind of things is visualized, more easier to understand. As you can see, we have two figures on the bottom, on the left bottom. One is showing the latency distribution across different message sizes. These messages are collected, whatever is used by the application during its run. And the other one is the distribution of the message size itself, with message count. So this one gives us an idea what kind of a range operation this application is using, as well as how the real latency is accumulating, as well as stats. Okay, and the table on the left, on the right, the light lower corner is more detailed exactly data if you are interested to looking for the detail for analysis purpose. And the next two slides will just show some of the two examples, use cases that use this tool to help us to do the performance for the end user to improve their performance for their application. And one of this is a deep lab, which we do this in TensorFlow. Okay, and what this is the end result after we using the tools. And as it turns out, when you're out of box, whatever that is, and for the whole software stack, and before that and after that, we can see the improvement is 30%. Okay, and speed up. What it turns out is we use these tools, we find out the key thing for this improvement happened to adjust some of the parameter settings for Highlevel, the fusion buffer, okay, the size as well as the time limit. Then this next one, we're showing another example. This is the ResNet 50. And this application, which is very popular used as a benchmark. And this one is on the PyTorch framework. Okay. And this is before and after we use this tool to analyze and do the optimization. And the end result is quite significant as well. It's improved 1.6, 90% of the overall execution time. Okay, and as it turned out, the key thing is to adjust some of the MPI layer parameters. Okay, and all this can be use the DI to understand and adjust. Okay. Now let's start focusing on the two new products we're trying to discuss. The first one is the MVAPICH DPU. And as we know that MPI is the dominant library used in HPC as well as AI applications for communication. And the requirement for this, especially for new technologies, if we take care of it from hardware and software perspective, we always try to maintain low latency and high bandwidth. And another thing keep in mind is especially with this tool, communication as well as computation, both of them are important part of your overall execution time. We try to achieve more overlap if it's possible, but we also have to be conscious when we try to do this overlap, try to avoid the resource conflicts between those two. Okay, we don't want to take too much resource away from those that can be used to speed up computation as well. So for CPU-based non-blocking communication progress, and that can lead to subpar performance because of the resource contention at the CPU. If we do use a separate CPU thread, okay, on the host to do this progress. So recently there's a new type of hardware, basically DPU, data processing unit, okay, which can allow us to do network offloading, the networking function of it. Okay, it's gaining attraction, and it has the potential to achieve better communication overlapping with the computation. So how do we take advantage of this? And this library is trying to achieve that. Oh, sorry. How come I jumped there? Okay, sorry. So this is a particular high-level architecture looking from the one particular DPU. This is NVIDIA's most recent Bluefield 2 DPU. As you can see from the on the right side, a node is connected, is mainly a whole bunch of processor core on some sockets, and with its own memory. Okay, and the DPU is externally attached to the host, and for this particular DPU, it has not only has a network adapter, which is a connected X6, okay, but it also has an array of ARM cores on that, which supports some kind of a general purpose programming capability. And that's what we're using for offloading, okay, some of the networking functionality. And for this particular one, the connected 6 has a bandwidth of 200 gigabits per second, supporting infinite band. And the ARM core on the SoC chip is a 64-bit V8. Okay. And it's clocked as 2.75 gigahertz. This is the latest chip from NVIDIA. And the local memory to the ARM is 16 gigabytes. So how do we redesign MPI library to take advantage of this resource? So, and we have just last weekend, we released the latest version of this MVAPICH DPU library. And it's all features is compatible, whatever is available in the MVAPICH standard release, open source release. This library is compatible to it and supporting all features available there. And the main thing here is we created, we use a new, a novel framework, okay, to do the offloading for, especially focused here on non-blocking collectives. And currently in this library release, we support both, we support all-to-all, all-gather, as well as a broadcast. In the future release, we'll add others important non-collectives as well. And as it turns out, this library can significantly increase the overlap up to 100% between the computation with any mix of our supported non-blocking collectives. And it's, as it turns out, it's actually accelerated the scientific applications which use the mix of these supported collectives. For this release is available from our company. If you are interested, please contact us for trial license. And the next few slides, I will show some of the evaluation performance and just show the capability as well as the benefit it brings. And this, to show this, this is the setup for the evaluation. Okay, we used a 60 cluster, okay, which has 32 nodes, each of them with an Intel Xeon CPU, and with 32 DPU attached to it as well. And so in total, we have 1K CPU cores and 256 ARM cores. And the configuration on the software side is, by the way, the CPU is Intel Xeon, this model. It's basically 16 core and clocked at 1.6 gigahertz. And the adapter from Bluefield 2 is what we mentioned before. The software we used in the test is Central's 8.3, and driver version is 5.2, and firmware version is 2430. Okay, and we use the latest release, and we'll use the micro benchmark as well as some of the some application to show the performance impact. Okay, so this is the overall execution time of OSU I2O micro benchmark to evaluate the efficiency of the performance impact. Okay, as we show two different configurations. One is 32 nodes with 16 ppm. The other one is 32 nodes with 32 ppm. And here we can see that from the overall execution, this is overall execution time bar, okay, where it contains both compute as well as communication time. And as you can see that as for this message range, okay, for lower, normally we are about the same, sometimes a slightly higher because of overhead for offload. But this is the major part that you can see the significant improvement on the latency, okay, and overall execution time, I should say. And that is sustainable on both lower count ppm as well as a larger count ppm. And this is the benefit we're looking at is about 20%, and sometimes higher, sometimes slightly lower. But it's very sustainable. And this has been turned out to be the case. And as the cluster size gets bigger, we expect the benefit becomes more significant. And so with that at the micro benchmark layer level to show the benefit, then people may have a question how much this can translate to real application. So for this purpose, we basically take a P3D FFT, which is one of the highly used compute kernels, okay, used in many HPC applications. The source code actually is from someone actually, the owner is in San Diego Supercomputing Center. Okay, this is open source, and we're using one of the version which actually use a non-collective auto, non-blocking auto, and so as you can see here again, we use the same configurations, and whatever we show at the macro benchmark level actually gets translated directly. And for the on the left, for a smaller size, the improvement is about 10 to 15%, okay, of that range. And on the right, you can see the improvement even more noticeable. Okay, well, one reason for that is because we are using the same size. And we, as you can see, the breakdown for the application evaluated here, we're starting P3D FFT input is a 3D dimension matrix. And each of this, we're starting with a size of 1K. And we looking at this different bars, each of them is double the dimension size once. So we double the lowest, then the second lowest, then the highest. Okay, and you can see this is very sustainable even for all these different sizes. And this, as it turned out, is actually very stable performance improvement. Okay, even for other sizes as well. And the next tool, we were just looking at some other collectives currently supported in the library. And this is for the all gather, and this is on 16 nodes. And the improvement is significant as well. And this is what we have been focusing on. Okay, here you can see that here we are looking at the two extremes. One is 1 ppm, the other one is 16 ppm. We potentially can go higher and 32 ppm as well. But for this set data, we did not show that. But the trend is the same. Its improvement is quite significant, especially for larger ppms as well. Okay, large node count as ppm. And if you're looking at the larger one for the larger size, I mean, for whatever we evaluate, it's about 40 to 50% improvement at a micro benchmark level. Okay, and again, this is overall execution time, allowing including both compute as well as communication. And this one is for non-blocking broadcast. As we know that broadcast is the base for all collective communication. And if we have a good base, then there's, I mean, all other collectives are a variation or added on or derivative of broadcast. Okay. And so as you can see here, the improvement is actually even more noticeable. And this gives us a foundation to build on for other variations of non-blocking collectives. And here you can see it's 50 or even 60%, depends on what the benchmark as well as the system size and the ppm count. Okay. Okay, so we also have some other features to come up, which directly support our accelerated DL training, which will come out in the next release of this library. It will support CPU-based DL training with DPU offloading. And it's actually, early result is showing that it's up to 15% improvement in the overall execution time with offloading enabled compared to without it. Okay, and it support this particular one support the PyTorch framework. And a paper with the basic idea on this has been published recently in the Hot Interconnect this year. And the design is based on the same idea, but we are doing that for our to be part of this library. Now, the last thing I touch on will be SCR XR. Okay, and so this itself is okay. Let me explain a little bit on the what is supposedly to be done. Well, is to be done for DL application for checkpoint. So the basic idea is you periodically doing a saving a snapshot of your training, so that you can resume or recover from it. The reason for that is because most of the DL model training require a long time to complete, to execute and complete. And it's not unheard of. Some of the training takes weeks or months to complete. And the other one is, if you make, especially these days, you make it distributed so that you can speed it up. Then you introduce more components, and it's susceptible to system failures because you have a larger scales, more components in this entire system. So as for at a high level, so for training, if you want to continue to be more productive, so you can reuse some of the partial work from earlier. You do some simple load and store for this, load the critical data, even some related stacks or things like that, for you to resume from that point. Okay, and how often you do this depends on your fault model. Basically, what's the average failure time to failure, this kind of thing. Okay, so you potentially can do it every and pack epochs. We pick the epochs because that's one of the recommended things from the framework, the PyTorch framework team recommended it there. So as for distributed training, it's similar thing. However, the simplest way to do this is because epoch, everybody is sending their values back to rank 0, and rank 0 combine them, then send it broadcast back to all the other workers. Okay, and so this is a simple sequence listed up here as recommended. So you basically checking everybody has sent the result. You basically, at the backup point. Then you save whatever is critical for your DNN, the parameters, all that type of thing, hyperparameter values. Okay, then you do a burial, make sure everybody reach that. And then once you've done that, you start to make sure that you potentially can tolerate errors during this point. Okay, shutdown or whatever. And then at the time you start up, you come back and see whether I need to resume. Or I have data to load so that I can continue my work. Okay, and so this is the basic pattern. And we're using this pattern to do the checkpoint. This is basically a general idea. Now, how do we speed this up to make it more efficient? And this is what SCR XR help us to do. Okay, it's this library itself is based on the open source SCR. One of the actually owner or inventor of SCR is Adam Moody, give a talk I think yesterday or the day before, I forgot. And he gave a lot more details on the design as well as the user interface. And today we're focusing on how we use this for applications from an application perspective. So this library is developed in collaboration with the team, the National Lab, Livermore National Lab. And the current library significantly increased the portability as well as scalability, flexibility, and supporting more the diverse type of job launchers, resource managers, and storage devices, etc. And it's customized as well as optimized for a range of systems, because each of the systems, their software stack is somewhat different. So the tools need to be adapted and configured to deal with different underlying protocol as well. Even the same software package stack can be configured differently in their system. So this will do that. Now, the other one is we enable fast and efficient restart and resume, like what I just illustrated a little bit back at the last slide. So we add support for launching applications where with spare nodes, just in case you sort of know the fault model, or at least how some of the often occurred model. Okay, then if that turns out to be the case, you run into one of those kind of fault. This tools will also automatically reconfigure and to restart and resume using the spare nodes after a failure if possible. Possible means actually it's some of the models you can tolerate, you predict and can tolerate. If the whole thing failed, then you won't be able to restart and using the same resource or allocation. So significantly, also, we significantly improve the maintenance of extendability by adding new Python binding as well as Python implementation of the CLI, which is a command line user interface, as well as APIs. And we actually also expanded support for DL and the machine learning frameworks as well as applications. Examples including PyTorch, Highlevel, and some of the application has examples to show. Okay, and part of this core code enhancement are done in collaboration with together with the Livermore team. Okay, and most of those ones are contributed back to open source. And this just give you an overview of the involvement of software stack, which the SCR Xer use. So on the top, you can see here first is distributed system. So it has multiple processors as well as multiple thread within the same node if necessary. Okay. And for each of the thread, and this is what it shows. Okay. And so you have the application at the top, then it uses the SCR for checkpointing, and it involved your database software or other IO local IO stuff, and it also interacted with IO for asynchronous for performance reasons. Okay, and as it turns out, this actually is one of the key things to deal with the future IO bottleneck, which actually existing today, but the future will be more critical. And all of that use a file system, and that interact with the storage system, which some of that is part of the globally shared file system, and others are local ones that is only accessible to that node. Okay. So we use all this mixing together. From SCR Xer perspective, you don't have to worry anything below that. It's all taken care of by the library. Okay, so the next few slides, we're going to show what this can do, what currently we can achieve for the DL. Okay, DL work. And basically here we already enabled it, this library to support Python. No, PyTorch. Two different type of this. One is Highlevel, the other one is the DP. Okay. We'll use two different AI DL applications. One is ResNet, the other one is a variation of that, EDSR. Okay, so this one, we have two applications or show. We actually convey the same type of thing, and it's all very convincing. Okay, but we also showing the same application use two different platforms. One is for DDP, the other one is for Highlevel. Both of them are on PyTorch. Okay. And so this is just a setup. So we're doing checkpoint for the application run. And here we do enable that for each epoch. Remember that based on your error model or fault model, this can be reduced based on your timing or whatever. Okay, but for this one, we're just assuming that's error model. We try to compare different scheme, how the overhead are looking like. Okay, and so for SCR actor, it will save the checkpoint to the local node, local storage. Then we only write from the local storage to the parallel file system every 10 epochs. So every 10 checkpoint you will save to the global file system. And as it turns out, as you can see, this is for, let me spend a little bit of time here. It's on the left lower corner. We have 3 bars of group. Okay, each group has 3 bars. The first one, the red one, is without checkpoint. Okay, and for this as a reference point, we'll just see how much the checkpoint itself created. That one overhead, how much is that? Okay, and we are comparing the 2 different checkpoint scheme. One is the naive one, okay, where you do your own stuff, okay, doing store and load. The other one is use our library. And as you can see that compare overall, this one is the checkpoint overhead itself is not that big, okay? And as it turns out, typically, even for SCR XR, it's about 10 to 15%, sometimes lower. And remember, this is, we're taking the checkpoint every epoch. And depend on that, this, you're doing this less frequent, this can be dramatically lower. Okay. Now, the second thing is between our comparison between the comparison between a naive and a SCR XR, as you can see on the right lower corner. The naive thing, the overhead is increasing significantly as you increase the GPU count. Okay. However, for the SCR XR, this is flat. It's maintained about 10 to 15%. And this actually stretch out, we'll see the next application to solve of GPU count. Okay. And so this convinces us this scheme, that this library is very scalable. And currently we're doing this test on the open power and using NVIDIA GPU. Okay, now to do it on the other platform we support, basically is a PyTorch over Highlevel. And as you can see, similar trend. Here, the overhead is slightly higher, okay, for SCR XR. Okay, it's about less than 20%. Again, remember, we can reduce the overhead by taking less frequent save point. Okay. And now let's looking at another application, DL application. Here, we have more precise computing, bigger data size actually. And as it turns out, we also run into a larger system size, which we scale it to 1K GPU device. Okay, and the trend is very similar. And still, we prove that this is scalable. The scalability of CR's Xscale is very good, and overhead can be controlled very well. Okay, it is maintained very well. Now, for different for this is a similar thing to see on the PyTorch over Highlevel platform. Remember, we have two different platforms. Okay, and this one is overhead. You can see is slightly higher. Okay, and one reason for that is because the DPP actually give us a lot more feasibility to do more of fine control on how we do stuff. And the Highlevel has less of control on that. A lot of things is behind the scene, behind the API. But regardless, this is still very good. And as we turned out to be that because there are multiple things working for us, one is we can maintain the overhead. And another one is because the multi-layer, it uses the local storage and doing less frequent global operation, global file operation. And yet another thing, which is behind the scene, that actually the backup from local to the global can be taken in a synchronous manner, which is totally oblivious of the critical path of performance of the application. And that's all. And hopefully that saves us some time. I'm open for questions and answers. I may ask some of my colleagues help answer some of the questions as well. Thank you.
Thank you, Donglai. So we are actually running a little late. So I would request all attendees, if you have any questions for this talk, please use the Slack channel.
Okay, we can take that. Yeah, sounds good.
Yes, thank you. So